Hello class and welcome to lesson 6.2 sinusoidal functions, Freddy the Frog. Today we'll be doing an investigation where you're going to be doing almost like a lab. So what you need to do is you need to go to your kitchen and you need to find about maybe 6 or 8 strands of spaghetti. So go do that, and while you're at it we also will need a glue stick as well as a protractor. Okay, so how about you pause the video, and then when you've got those, please come back. Okay, after the pause, ladies and gentlemen, so today we're going to take a look at an investigation, hopefully you've got your supplies with you now, of Freddy the Frog riding a mill wheel. Okay, so many old flour mills, and I know there's one still in Arva that uses water power in order to pound or to create the flour, okay? And mills can use that as well, just to generate some power. Anyway, so what we're going to do is take a look at this wheel. So up at this diagram on your handout, Freddy's going to start here, okay? And Freddy's going to travel each different measurement. He's going to go here, and then here, and then here. So Freddy's going to travel on the water wheel. And what's going to happen is he's eventually going to go down below and come back up, okay? All right, so it says, Freddy the Frog is riding on the circumference of a mill wheel on a mini putt course as it rotates counterclockwise. He would like to know the relationship between the angle of rotation and its height above/below the water surface. Just keep a reminder, guys, that if he's down here, he's going to be below the water, so his height's going to be negative when you take a look at it, okay? A scale diagram of the wheel is shown, okay, down below here, and the actual wheel has a radius of 1 meter. So what does that tell us, folks? When Freddy the Frog is way here at the top, that tells me his distance is 1 meter. He's 1 meter above the water. Likewise, when Freddy the Frog is at the bottom, he is negative 1 meter, or 1 meter down into the water. Okay, your task is to use dry spaghetti to help you determine the heights at various points of the circles. So first of all, it says to make a hypothesis here. So let's hypothesize for a second. Draw a sketch of what you think the graph of angle versus height below and above the water would look like. Well, first of all, what do we know if this is the water level? Okay, and as we do our angles, so this is going to be our angles. Okay, in terms of degrees, and this is going to be our height. What do we know? We know that Freddy starts at water level, okay, and Freddy is going in a counterclockwise motion, so he's going up in the air to a maximum of, we know he's going to a maximum of 1 meter, then he's going to come back down to the axis, which is right here, and then he's going to start to go down below the water, and he's going to come back up. But we say we're going to do 2 rotations, so he's going to follow the same pattern. He's going to go back up to 1 meter, come back down to water level, go down to 1 meter, and finally come back up. Okay? So just to complete our graph, what do we know? We know that his minimum is going to be negative 1 meter because he's going to be in the water, and his maximum is going to be 1 meter above. So we know the amplitude is 1. Okay, and what else do we know? The time it takes to complete one period or one cycle, okay, is going to be how many degrees in this circle, folks? It's going to be 360 degrees. Okay, so 360 degrees. So what does that tell me? Halfway through, he's going to be at what? 180. All right? So what I want you to do, folks, is I want you to, step 1 is to line a protractor up on this circle that we're asked to use. Okay, I'm just trying to bring it up. Okay, so you line a protractor up and mark off every 15 degrees. I know the first one's done for you, so you make a little tick mark here, 30, 45, etc. So keep making those marks. Okay. Let me move that off so you can explain what's going on. What we do know is that the hypotenuse in every case, guys, will be 1 because that's the radius of the wheel. Okay, 1 meter. So what we're asked to do is we start here, and Freddy's here. What height is he? Actually, he's at 0 height. So when you put that up, when you start your graph or your grid on the next page, there's going to be no spaghetti string or no spaghetti on that one. Then you mark off 15 degrees. So what you're going to do is put the base of the spaghetti here, go here, break that off. So I would actually tell you to do two at the same time because he's doing two revelations. So that would mark off 15 degrees, and the next one, which would be 360 plus 15 degrees, which would be 375. Okay, and glue those on right away onto your graph on the next page. Then I want you to take a look at the second one, so 30 degrees. So for 30 degrees, ladies and gentlemen, you're up here. So again, you draw the height here, and then you break that off again with using the spaghettis, and that's going to be, I would break two of them off for that measurement. And then what you're going to do is actually build a graph with different heights, and you're going to find some patterning as you go. So after you glue those two, do the next two, and then keep going and keep going. And remember, folks, that you're going to do this all the way around, all your 15s, all the way around, even when we get to the negative where he's in the water. So if I move this, don't forget, 15 below, 30 below, 45 below, all the way around until you come back to his original circle. So basically, you're going to be collecting a lot of pieces of broken out spaghetti string. So the strategy is, as soon as you break it off, glue it on so then you don't lose its place. All right? So what you should do is, after you've done that, you should be gluing these on. For example, we start at 360, okay? The first height that you, or first spaghetti string that you should have cut off should be this height, as well as you do the same at 375. Which is this height, okay? So that's the first one. And the second one you should have done should have been at 30, okay? Which are these two, okay? And as you do this, you're going to develop a pattern, okay? And this pattern, ladies and gentlemen, after you've completed all your spaghetti strings, it should look like this, okay? And just keep in mind that when you get to him being in the water, ladies and gentlemen, this value and this value, if I've drawn it to scale properly, is the same as his height above. However, it's drawn down because he is under the water in this section. So this is where he's under the water. So that's why it's kind of negative. Okay? All right, so hopefully you had fun doing that investigation. Got a couple questions for us to answer on the next page. So again, check your spaghetti strings. They should look like that. Okay, so on your graph, draw a smooth curve connecting the tips of the pieces of spaghetti. Try that if you can. I know that that's not the easiest thing to do because sometimes the glue will break off the spaghetti. So just try your best on that one. 2, describe the graph made by Freddy the Frog traveling on the mill wheel. Hint, use some terminology that you learned yesterday. So what we learned about is the time it takes to complete one rotation. That's what we call the period, and it's 360 degrees. The equation of axis, that's basically where the spoke or the center part of the wheel lies. And if you take your maximum, which is 1, and you add your minimum, which is -1, and divide by 2, you will get y equals 0 is your axis. Next thing we've learned is the range. Okay, the range deals with the minimum value to the maximum value, as well as the amplitude. The amplitude is the maximum, subtract your axis. I'll just write that in there in case you have forgotten where that comes from. Sorry, sometimes let me sneak a little s in there, okay? All right, so given the diagram that is not to scale, describe another way to determine Freddy's height when the wheel well is rotated 15 degrees. So if I quickly erase this, ladies and gentlemen, what do I know? I automatically know that the radius is 1 meter, which is our, if you could argue, it's the hypotenuse, and we know we've got 15 degrees. Remember, the original formula for sine is that sine theta equals the opposite over the hypotenuse. In this case, our hypotenuse is the radius. Okay, so looking at 15 degrees, the sine of 15 degrees equals the opposite side, which is our height. That's what we're trying to find, over our hypotenuse, which is 1. Okay, and then if we just rearrange and let the opposite equal the height, we can come up with this formula that the height equals 15 degrees, the sine of 15 degrees. Okay, so it says to take that and determine Freddie's height for each of the following angles using the method you described above. So at 15 degrees, the height equals sine 15 degrees. Plug that in, and compare that with your spaghetti strings. See how accurate it were. Okay, the sine of 30 degrees. Hopefully you recognize that as a special. My fault. Yeah, a special triangle. Okay, and so you should know that that's half, so you should be halfway there. Sine of 45 is 1 over root 2. Again, it didn't ask you to leave it as a ratio, so you could just give it as the value. If you were leaving it as the exact value for the ratio, don't forget to rationalize here. So if you were to rationalize, you'd multiply the numerator and the denominator by root 2. Okay, and for D, sine of 60, another special triangle. It's root 3 over 2, which gives you those measurements. Compare those heights with your spaghetti strings and see how you did. All right. Okay, compare your results with your spaghetti heights, and what should you notice? You should notice they're the same. And you're going to say, hey, Ms. R, that was a fun activity, but why the heck did we do that? We did this to introduce what's called one of your basic or parent functions of this unit for sinusoidals, and it's called y equals the sine x curve. Okay, so please fill in here, guys, that key properties for f at x equals sine x. Okay, and we're talking about between 0 and 360 degrees. So one thing to notice about sine x starts at the origin, it then goes to its maximum, back to its axis, to its minimum, and then back to its axis. The amplitude for this base function is 1, the period is 360s, your x-intercepts occur at 0, 180 and 360, but notice I've got dot 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 in front of it and dot 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 after it. Just remember that this is a continuous function, so it will go from negative infinity to positive infinity, so it keeps going on. So how do we state that? We just say that the domain is such that x belongs to a set of real numbers. The maximum, ladies and gentlemen, is 1, the minimum is -1, so to do our range, it's from our minimum to our maximum. The graph is increasing, okay? Increasing between 0 and 90 degrees where it's going up, as well as from 270 to 360. Okay? The graph is decreasing or on a downhill slope from 90 degrees to 270 degrees. That is one of the parent functions of sinusoidals. Just remember, guys, that sinusoidal function is any transformation from the sine x curve, the one we have here, or the cos x curve, which we're going to learn in a minute. Okay, so this is the basis of the unit. And just remember, guys, in past units we've dealt with the A, the K, the D, and the C. So how do we shift left, right, up, down, flip, reflect, stretch, compress? All of that we're going to be dealing with in terms of these waves. Because they're a different property, that's why we investigate this as a separate unit. Okay? All right, so create the graph of cos theta. So what I want you to do, guys, is in your calculator, I want you to say 0 degrees and go cos of 0 degrees. And what you'll find out is that it is at 1. Okay? I would like you to say, hey, cos of 90, plug it in your calculator, and you'll get 0. Okay? Press the cos of 180, and you should get -1. Okay, press the cos of 270, plug it in your calculator, and you should get 0. And plug the cos of 360 in, and you should get back to 1. So cos x, or cos theta, is our second parent function. And what do you notice? It's a little different. It's a little different than your sine x. It's actually a shift because it doesn't start at the axis, it starts at its maximum. Okay? And we're going to explain the direct connection to them in future lessons, but let's just take a look at the properties of this cos x. Okay, again, to find these, you can just plug the values into your calculator, that's fine, or you can just learn a shortcut way of doing things. Okay, so here is the key properties of our second and our own, like there's only two parent functions for this unit, guys. So cos x, okay? One thing to know, the cos x is the one that's drawn in blue, okay? I have just drawn the sine x one just to compare the two parent functions, okay? So looking at the blue one, just draw your blue one in. Don't worry about the red one. It's just easier to see with the red. Okay? So the blue one, the difference between cos x and sine x is that cos x goes max, axes, min, axes, max. Okay? So we have the same order, except we just, instead of starting at the origin or starting at your axis, you're actually starting at your max. Many things are similar about it. The amplitude is still 1, the period is still 1, the domain is still the same, the max, min, and range are the same. However, what's different in this case are your intercepts. Okay, so remember we got dot, dot, dot because the domain belongs to a set of real numbers. You can have intercepts before 90 and you can have intercepts after 270. Okay, what else is different is when the graph is increasing and decreasing. Okay, this down below is just what we did on the other graph by just plugging those values in, ladies and gentlemen. Okay, so hopefully that gives you a good understanding of what sinusoidal functions is. We will learn, ladies and gentlemen, that in future lessons, if we take the cos x curve and we add or shift it 90 degrees, it's going to equal the sine x. Okay, so let me just write that in so you know that. Okay, so if I take cos x, and if I'm going to shift it 90, it's going to look like x minus 90 degrees. Okay, that's going to equal your sine x. Okay, so your one parent function equals the other as long as you shift it 90 degrees to the right. Okay, and that's why I wanted to show you the two of them. Again, you always, once you get started, you follow the same pattern. Depends on where you start though. Okay, so you're always going to be drawing probably 5 key points, and you either start at the axis, go axis, max, axis, min, axis, or you start your max and you go max, axis, min, axis, max. So you're still developing the same patterning. But again, to relate one to the other, there's a 90-degree shift. Okay. So for tonight's homework, guys, hopefully you've had fun with the activity. Let's read page 357 to 362. Develop a better understanding, and you're probably going to want to have some colored pencil crayons or colored markers for next class when we're doing some sinusoidal transformations. Have a great day, folks, and see me if you need any help. Okay? Bye.